Just like what we did for limits and continuity, given two functions f and g that are differentiable at a point C, we would talk about the derivative of f plus g, fg, f by g, etc. So let's state what we have. So let I subset of R be an interval, and f from I to R and g from I to R be functions that are differentiable at C. Then, first of all, we can say that if alpha is a constant, that means alpha is a number in R, then alpha f is differentiable at C. And moreover, alpha f dash at C is equal to alpha into f dash at C. This is very easy to see. What you have to do is you have to look at limit x tends to C of alpha f of x minus alpha f of C divided by x minus C. So we can just take alpha common and take it outside the limit. That's all. So we get alpha into limit x tends to C of f of x minus f of C divided by x minus C. Now this exists because f is differentiable at Z, and because of this, this is equal to alpha into f dash of C. Okay, so that's all. Similarly, we can say that f plus g is differentiable at C, and f plus g dash of C is equal to f dash of C plus g dash of C. Again, it's very simple. What we are interested in is limit x tends to C of f plus g of x minus f plus g of C divided by x minus C. So just using the definition of f plus g as f plus g of x is equal to f of x plus g of x, we can just rewrite this as limit x tends to C of f of x minus f of C by x minus C plus g of x minus g of C by x minus C. Now we can just use limit theorems and say that that quantity is equal to this. And thus we have the result for f plus g as well. Now we will look at the product of two functions, and hence this part of the theorem will be called as the product rule. It says that fg is differentiable and fg dash at C is equal to f dash at C into g of C plus f of C into g dash of C. Now let us prove this. How do we prove this? We are looking at the limit x tends to C of fg of x minus fg of C divided by x minus C. Now we know that fg of x is nothing but f of x into g of x. And you have seen this trick many times. What I do is I will subtract f of c into g of x and add f of c into g of x to this. So I get something of this form. Okay, so that can be rewritten as limit x tends to C of g of x into f of x minus f of c divided by x minus c plus f of c into g of x minus g of c divided by x minus c. So it's the limit of this whole thing. I'm just doing some algebra on whatever was there above. That's all I did, right? So I took g of x common from these two. That's what I did in the first stage. So that's the g of x here. And then I wrote f of x minus f of c divided by x minus c. And then similarly, I took f of c common from these two. So I wrote it as f of c into g of x minus g of c by x minus c. But now we have something interesting. Notice that now g of x is limit of x tends to c g of x exists because g is continuous. Why is g continuous? Because g is differentiable. Because of that, this limit exists. Similarly, this limit exists because f is differentiable. This is a constant, and this limit also exists because g is differentiable. So because of this, the limit of all these things exist. Hence, this limit exists, the total limit exists, and this limit also exists. So using limit theorems, I can first write this is equal to limit x tends to c of g of x into f of x minus f of c by x minus c plus limit x tends to c of f of c into g of x minus g of c by x minus c. Let me just clean this a little bit. Now again, using another limit theorem, which is limit of product is equal to product of limits, we get this is equal to limit x tends to c of g of x into limit x tends to c of f of x minus f of c by x minus c plus limit x tends to c of f of c into limit x tends to c of g of x minus g of c divided by x minus c. Now notice that this is equal to g of c, this is equal to f dash of c, this is equal to f of c, and this is equal to g dash of c. And thus we have the theorem. Finally, if g of c is not equal to 0, then f divided by g is differentiable at c, and f by g dash of c is equal to f dash of c into g of c minus f of c into g dash of c divided by g of c the whole squared. To prove this, we look at limit x tends to c of f by g of x, which is equal to f of x by g of x minus f of c by g of c whole divided by x minus c. Now here notice that we have g of x in the denominator, and that we can make sense of that if and only if g of x is not equal to 0. So why can we take f of x by g of x? G of c is not equal to 0 and g is continuous. Why? Because g is differentiable and differentiable functions are continuous. So g is continuous. So because g is continuous and g of c is not equal to 0, we can find a neighborhood of c such that if x belongs to this neighborhood, then g of x is also not equal to 0. So whatever, because we are taking limit x tends to c, we can take such a neighborhood and assume that our x lies inside such a neighborhood. And that is why we can do everything that we are doing. Okay, so we can simplify this as follows. We can write this as limit x tends to c of f of x into g of c minus g of x into f of c whole divided by g of x into g of c into x minus c. Now just like what we did to prove product rule, we will add and subtract something. So this is equal to limit x tends to c f of x into g of c minus f of c into g of c plus f of c into g of c minus g of x into g of c divided by g of x into g of c into x minus c. And that is equal to limit x tends to c of 1 by g of x into g of c multiplied by g of c into f of x minus f of c divided by x minus c minus f of c into g of x minus g of c by x minus c. Notice that this 1 by g of x into g of c is part of both the terms, so we have to put a common bracket. Finally, notice that this limit exists, like limit of x tends to c 1 by g of x into g of c exists because g is continuous. This limit exists because f is differentiable, and this limit exists because g is differentiable. So just like what we did earlier, we can use the limit theorems to separate these limits. We can add limit on each of these independent terms, and this converges to 1 by g of c the whole squared. This converges to f dash of c, and this converges to g dash of c. So together we get the required result, which is f by g dash of c is equal to f dash of c into g of c minus g dash of c into f of c divided by g of c the whole squared. By the way, I forgot to mention this result is called quotient rule.